very much for the introduction, and also thanks to the organizers for giving me the opportunity to talk here about geometric functionals of polyconvex excursion sets for social noise processes. Okay, so a long title, but so the plan for my talk today is, so I start with introducing the main concepts at first. So I will introduce what are social noise processes, of course, at first, and then what are excursion sets of social noise processes. And then I will introduce a model for which these excursion sets are polyconvex, which basically means that we can write them as a finite union of convex sets. And why do we do this? We do this because we want to calculate geometric functionals of these excursion sets, which are then only defined for polyconvex sets. And then we are interested in the asymptotic behavior for expectation, variance, and of course, at the end, the central limit theorems for growing observation values. Okay, so that's the plan for my talk. I start with this setting. So we have here an underlying marked Poisson process, eta, on some space Rd times M. So we have random points in Rd, and M is some marked space. And we have an intensity measure, which is gamma lambda d times q, where lambda d is the Lebesgue measure, and u is just some probability measure. Okay, so this is our underlying marked Poisson process. And then we can define for social noise processes as follows. So what we have are these kernel functions gm, which are non-negative, and for these gm, we define the social noise process at point y as the sum. So we sum here over all points of the Poisson process and have here in the sum gm of y minus x. So this mark somehow indicates which function we use, and here we insert this point x in Rd. So that's the idea of a Poisson noise process. And now for different dimension, we could have pictures like this for dimension 1 or for dimension 2 like this. And now what we are interested in are excursion sets. And excursion sets means we want to look where is our Poisson noise process larger than or equal to some threshold. So in other words, we want to look at all y in Rd such that this sum that you just saw is larger than or equal to some u, and u is now throughout the whole talk just some fixed constant. So in the pictures we had, for example, for u equal to 5 here, the excursion set would just be here, this red part. And for the other picture that you just saw, this was the picture that you just saw, if we want to look now from above onto this picture, and let's say we want to know where it's larger than or equal to something like 15, we would get such a picture where the red region is now the excursion set. So these are the objects we work with, somehow these random sets. And as I said, what we want to do at the end is we want to consider geometric functionals of these random sets on some observation window W. And to be able to do this, we want that these random sets are almost surely polyconvex. And to make sure that this is indeed the case, we need some additional assumptions for these kernel functions gm. So what we have additionally now is that they are concave on their compact convex support, and by support I always mean now the closure of all the points which are mapped to non-zero values. So we have such a compact convex support, and gm is concave on this support. And then, of course, we want to have something like volume of km is larger than 0, and we have some continuity condition of gm on the support km, which basically means that on the boundary, so this is mainly a condition for boundary points. So what we could do is we could do on the boundary of the support, we could jump to 0. So this is mainly a condition for the boundary points. Okay. So these are the conditions for the kernel functions. And what we also need are moment conditions of this form. The I are here intrinsic volumes, and what we want to have are moment conditions of this form, that they are, the kth moment is integrable. For the moment, we just need k equal to 1. Later on, if we talk about asymptotics of the variance and the central limit theorem, we will need also second order and fourth order moment conditions, but for now we just have the first order moment condition. And this first order moment condition now gives us the following. So it tells us that somehow the number of points in this SW is almost surely finite. And what is SW? SW are basically all the points which could influence our excursion sets. So in other words, we look here at all points such that this shifted support somehow intersects the observation window. If you remember in the sum, we always had gm of y minus x. That's the reason why we have here this shift. So it's really the idea that we look at all points which, as I said, should could somehow contribute to the excursion set. So where gm of y minus x is not always 0 on the whole observation window. Okay, and so this means the only points that we need are actually in this set. And if we denote these points now by x1, m1 to xn, mn, then what we can do is we can write the excursion set on the observation window as such a union. And what do we do here? What we do is we take here all possible combinations of points which could influence the excursion set, and then we look at all y in W such that the sum is larger than or equal to u, and additionally somehow this g and j of y minus xj is not 0. That's somehow this part. And well, if we now go through all possible combinations of points which could influence the excursion set, then the union of these sets give us the whole excursion set. So what you see here is we can write this excursion set as such a union. And why is this helpful? Well, because with the concavity of these functions g, m, j, we can show that these sets that you see here are convex. So what you see here is a representation of the excursion set as a union of convex sets. So this shows us that since n is almost surely finite, we can write the excursion set indeed almost surely as a union of finitely many convex sets. So in other words, they are almost surely polyconvex. One specific example, which is also included in our model, is the so-called Boolean model. I guess probably most of you have heard from the Boolean model. This would here just correspond to taking the union of all the supports that we have, or the shifted supports that we have. And we get this model just when we set gm of x just equal to u or larger than u, because then the excursion set is of course just the union of these convex sets. In general, this is in some sense a bit easier, this model, than the general case of excursion sets. And I will go more into detail later on why that is the case, but I will already give you here the idea, what we need later. For the Boolean model, as I said, you just take the union of these shifted supports, so you have a union of n convex sets. Here, what you see is we take a union of up to 2 to the n convex sets. So we need here maybe more sets in the general case than just n sets like in the Boolean model. And why this is a problem is what I tell you in a few seconds. But already keep this in mind. We need here something like 2 to the n unions, and here only n. Okay, but for the moment we have now this model, so we can define geometric functionals. So what do I mean with geometric functionals? I mean a measurable function which is translation invariant. So I can just shift my sets. It's additive, so I have such an inclusion-exclusion principle, and it's locally bounded, so the absolute value of phi of a is bounded by some constant for all convex sets in 0, 1 to the d. The probably most prominent example that you probably all know are the intrinsic volumes, but we can of course also have other examples. So if you look here at the definition, what we, for example, do not need is something like rotational invariance. So yeah, we have here also, of course, other examples, but as said, most prominent examples are probably the intrinsic volumes. Okay, now let's go to the result. So, as I said in the beginning, we want to let the observation window grow. This means we consider WR, so R times W, and want to let R go to infinity. And now under the first order moment condition, what we can show is that the expectation for such a geometric functional of the excursion sets behaves like the volume of the observation window. And we can actually also calculate such a constant. A similar result was also shown here in this book from Schneider and Weil for so-called standard random sets, where Z is such a standard random set. And you can probably already guess what's the problem now. The problem now is that our sets are in general not these standard random sets. And now we get to the point why taking the union of 2 to the n points is maybe too much. Let now n of a denote the smallest possible number such that we can write a polyconvex set as a union of convex sets. And now what we have as a condition for standard random sets is that this expectation is finite. So we have here 2 to somehow the number of convex sets. We need to write z as a union of convex sets in 0, 1 to the d. And this expectation has to be finite if we talk about standard random sets. But as I've shown you, our excursion sets can be written as a number of up to 2 to the n convex sets, and n was the number of points in this SW, which is then Poisson distributed. So expectation of 2 to the something which can be up to 2 to the n is then maybe not finite anymore. And that's the reason why this is not in general a standard random set. Of course, you could argue now, well, maybe my construction was just not good, and we could find maybe a better way to write my excursion sets now as a union of less convex sets, because we just need the minimal number. So let me give a brief example to really convince you that this expectation is not necessarily finite. So we can just look at such a simple example as kernel functions being equal to u half on the whole support. So they're constant and 0 everywhere else. And then if we have configurations which look like this, so we have n half shifted supports which look like these blue regions, and n half regions which look like this orange regions. Then you see here, of course, we need 2 supports to overlap to be larger than or equal to u half. If we add this, larger than or equal to u, to add to get larger than u. So this means the dark red region that you see here is now the excursion set in such an example. And as you can already see here, now we need something like n half times n half, so n squared over 4 convex sets to write this dark red region as a union of convex sets. So this number that we need is something like n squared over 4. And now if the probability for such configurations is large enough, it's already sufficient, this n squared over 4, to guarantee that then this expectation is not finite anymore. So yes, so this was just the short example to convince you really that we really have a problem. And now I of course have to tell you how to solve this problem. And for this I show you at first for the proof idea of the expectation how the proof idea usually works for standard random sets. So what we can do for standard random sets to show the existence of the expectation is that we just use that phi a is bounded by some constant for all a subset of 0, 1 to the d. And what we do now is just we write this standard random set on W as a union of capital N convex sets. And then we use here something like the inclusion-exclusion principle to this function phi, so that we have here somehow a sum with alternating signs of 2 to the n sums. And well, now we just say we can bound each of the summands by this constant m, And this is just the number of symbols we have in the total inclusion-exclusion principle. And if this expectation is finite now, of course, we are done and everything is fine. Since we cannot do this, what we do instead is a dynamic decomposition. This means what we do is we want to cover the whole observation window now with cubes of length 1. And now we somehow want to control this capital N. And how we control it, we just look at each cube and we'll just count how many convex sets do we need. And if we need more than some constant L sets, we divide this cube into 4 cubes. And then we check again for each single cube. Do we need still more than L sets or do we need less than or equal to L sets? And now, for example, if we need more than L sets still for these 2 cubes, we divide them again. And well, we continue dividing these cubes further into cubes until for each cube we have the condition that this number, capital N, is smaller than or equal to L. Why does this help us? Well, now this helps us because now on each cube we can easily, of course, control this number because it's bounded by L. And what we can also, or what we also have to consider is, of course, the boundary here. But since, well, the cubes only overlap here at the boundary, this is also something we can control and work with. And of course, finally, we also have to control the decomposition, but that's also doable. And if we put all 3 things together, we also get the existence of the expectation, and then we can show the result that you just saw. Okay, so that's here really the main difference, this dynamic decomposition, compared to previous work, for example, for standard random sets. And we also use such a dynamic decomposition also for other results. Now, if we continue, for example, for the variance, what we can show is that under now a second order moment condition, we can show that the variance somehow in the limit behaves like the volume of the observation window. So this fraction converges to some sigma naught, which actually also has an explicit representation. And well, we know it's larger than or equal to 0 for the general case. And of course, the question arises, when is this indeed larger than 0? And this is part of my work in progress. So what I plan to show and hopefully show soon is that if the geometric functional can be written as such a linear combination of intrinsic volumes, and well, it's not constantly equal to 0, then that this limiting sigma naught is larger than 0. You just saw in Anna's talk how complicated it can be to show such a lower bound for the variance, and I actually also use a generalized version of what she did. And so far what I can already show is for just the intrinsic, for a single intrinsic volume, it's quite fast to show that it's positive. If I restrict the family of kernel functions I can use, then I can also show it already for the whole linear combination, but there are still some parts missing for the complete general proof here, so that's why I call it work in progress. But I would hope that this should, so I think it should also work in the general case for geometric functionals which look like that. Okay, so this was the variance. And now to conclude, of course, I introduce the central limit theorem. So therefore, let n be a standard Gaussian random variable. And we have a fourth order moment condition. What we can show now is that the distance of such a standardized random variable compared to the Gaussian random variable is bounded by some constant over square root of the volume of the observation window. So in other words, it's somehow what we would expect, something like square root of the variance. And well, we can show it here for Kolmogorov and Wasserstein distance. A similar result actually, or the same result actually for the Boolean model was already shown in this paper from Klaas and Schulte in 2016, and you can also find some results here in this book for the Boolean model. There are of course also already results for prosocial noise processes and excursion sets of prosocial noise processes. I've only listed here these 4 papers where you can also already find results for specific geometric functionals like the volume or also something like Euler characteristic. And usually the differences in this paper is just that we have different conditions on the kernel functions GM, so they may be a bit, the behavior of the tail usually of the kernel functions differs here in these papers. And well, with this, I'm actually already done. So thank you for your attention.